Good morning, everyone. Good afternoon. Good evening. Good night. Depending on whenever you're watching this, one of those hopefully applies to you. If you haven't already, go ahead and pause this and get out lesson 11, filling containers. We're jumping modes, and I wonder if I can go back here. If you haven't noticed, we're kind of jumping modes. This unit 5 is all on functions and volume. So we've done nothing but talk about functions, tables of functions, equations of functions, graphs of functions, stories of functions, linear models of functions, piecewise linear functions. And then we're starting to get into now volume. You'll notice filling containers, how much will fit, volume of a cylinder, finding cylinder dimensions, volume of a cone, finding cone dimensions, scaling 1 dimension, scaling 2 dimensions, estimating a hemisphere, which is a half of a ball, the volume of a sphere, and finally cylinders, cones, and spheres all together and putting it all to work. So you can see we're still talking, all these are still kind of functions, the equations, but we're kind of going to leave that terminology out of the way for now and just get back into volume. So today's lesson, that one, is just kind of remembering what volume is, kind of how it looks, how it feels, and essentially kind of how it is a linear in some regards. In some regards, today's will be linear. So if you look at the warm-up, it says which one doesn't belong. There are 3 drawings of dimensional objects. Which one doesn't belong? Explain your reasoning. Well, as usual, each and every one of these you could argue doesn't belong. You could say why A doesn't belong, why it's different than B, C, and D. You could say why B is different than A, C, and D. You could say why C is different than A, B, and D. And you could say why D is different than A, B, and C. And if you could try to be a little more creative, and maybe you actually are, but I know many people always say D doesn't belong because it's the only one that doesn't have any curved sides. And that's fine. That's great that you're at least recognizing. And by the way, you haven't dealt with finding the volume of anything with curved sides yet. So I always like this unit because it is some brand new formulas you've never seen. But if you could take a minute to write down just real briefly why you think A doesn't belong, or B, or C. And if you can't think of a reason, then go ahead and stick with D. Hit pause if you need to, otherwise we're going to move right on to activity 1. It says your teacher will give you a graduated cylinder, water, and some other supplies. If you want, I have given you a link to a graduated cylinder. If you look right here, it'll look similar to that. It might be built into your curriculum right here. So if you clicked on lesson 11, you'll notice you can scroll down and you'll see it right there. I'm going to use it over here. But nevertheless, it says your teacher's going to give you those. So it's going to just be a digital version of it. And you'll use these supplies to investigate the height of water in a cylinder as a function of the water volume. Again, a math teacher, that doesn't make any sense to me unless I reword it. And if I take out the word function and put it the word depends. So it says the height of water. I'm still on the straight line. The height of water depends on the water volume. Investigate how the height of water, or the height of water in a cylinder, the height that the water is from bottom to the top, it all depends on how much water is in there, how much water volume. Yeah, that makes sense. The more water that's in there, the higher it's going to be, the less water. So, okay, yeah, that's got to be a function. The height does that. So I guess we're going to investigate it. First off, it says make a prediction about the graph. Well, first off, kind of give us the answers, but here's the graph down there in question C. It says create a graph that shows the height of water as a function. If you remember, the y-axis is always the dependent. Y always depends on x. Or whatever they say, if something is a function of something, this y is a function of the x. So if the height of water depends on the volume of the water, then this is going to be, the height is going to be dependent on the volume, meaning the volume is the, whoa, why did I add an extra letter there? Volume. That's the independent. That's the thing that we change. So we can change how much water we put in there, and what will depend on how much water we put in there will be the height. So we kind of answered part of C already, but now we need to think about the shape of the graph. Do we think the shape's going to be like this? Do we think it's going to be like this, or like this, or is it going to be a curve like that? What do you think? Whatever you think it is, go ahead and write down. Do you think it's going to be a curved line, a straight line, whatever it is, write it down. I guess those are the two options, curved or straight. And then we'll see what happens. And then it says fill the cylinder with different amounts of water and record the data in the table. So again, you could do this on your own, but I'll go ahead and give us some data that we can put down. So here we go. Here is a cylinder. It says it is 2.5 diameter, 5 centimeters. There it is. It's 2.5 centimeters for the radius, which means it's 5 centimeters altogether. A radius is half of a diameter. So it's 5 centimeters all the way across. I'd drawn it if I could, but I guess I could. And the height is 6, but that's kind of irrelevant because right now we'll measure the height. It'll tell us the height as we add. So we're going to add some water to it. I'll fill it, and then I'm just going to pause it. And it says right there that the height is 1.3. So I'm going to go back here, and the volume is 24.9. So the height is 1.3, and the volume is 24.9. 1.3, 24.9. Now we're going to go back here, and let's get some more pieces of data. Let's fill it some more, and stop. So now the height is 2.9 and 56.7. So we're going to write 2.9 and 56.7. I guess I should have said, if I really wanted to, my initial one, I should have said the volume, when the volume is 0, the height is 0. That's always a worthwhile piece of information, just because that is, if you remember, is proportional, it always starts at 0, 0. And let's go ahead and just do one more. Fill it up some more, and yeah, let's stop right there. The height is 4, and the volume is 78.7. So let's write a height of 4, and it's 78.7. And that should be enough. So if we were to graph that, you'll notice the biggest piece of information is 4. So we would write a 4, create a graph. That means half of that would be 2, which means in between would be, whoa, I did not draw 2 halfway between. Thought I did. maybe further down there, which means that's 1, 2, 3. And our biggest piece of information is 78.7, so that means somewhere over here is going to be the biggest piece of information we need is 80. And half of 80 would be, excuse me, volume. I'm going to write you a little further down here. That would be 40, which means right here is 60, which means right over here is roughly 20. And I should have said this already, but you guys can pause this video whenever you need to. If you need to get caught up or think about something, of course you have that option. Just hit pause and then hit play again when you're ready to rock and roll again. But so anyway, any halfway between all those would be, obviously, here would be 10, 30, 50, and so forth. Sorry about that. And that would be 70. Okay, so let's graph some of this. If the height is 1.3, the volume is 24.9 or 25. If that's 20, that's 30. 25 is in between. 1.9 is going to be almost right at, or no, I said 1.3. So 1.5 would be halfway between there. So we're going to have a dot somewhere right around there. And at a height of 2.9, which is almost 3, that's going to be 56.7, which is darn near 60. So that's going to be somewhere right up here. And then at 4, it's at 78.7, or darn near at 80, which is right here. And you're going to notice, if we actually did this exact, guess what? We're going to have it an exact. This is, by the way, linear. This is not, oh, we're off. The only reason why we would be off is because it's water, and maybe we're not measuring it to the nearest 1/100th of a milliliter and 1/100th of an inch. But notice how we just kind of made a very rudimentary graph, and it darn near came out straight, because it will be straight if you actually did this. So guess what? Not only is the height dependent on the volume, not only is the height the function of volume, it's a linear function. This is not only a function, it's linear. And it makes sense, because if we go back to our picture, guess what? The more water we add, it goes up by the exact same amount. In other words, if we, I keep pushing on that one. If we were to find the slope of this line, it'll tell us the height per, I guess we should say, this is in centimeters, the number of centimeters it goes up for every milliliter. Remember, the slope always gives us a rate of change, so that'd be centimeters per milliliter. Every milliliter, I'll tell you exactly how many centimeters it goes up. Now, watch this real fast. What if I switch this? I'm going to hit reset, and let's make this super wide. Look at the, whoa, I didn't do that. Come on now. Oh, man. There, let's make the diameter 10 centimeters. The height is the same, but we've just made this really wide. So if I start filling this, let's go ahead and write down some data. Boom, whoop, I said pause. There we go. So volume is 201 when the height is 2.6. So let's go back to our graph. 2.6 and 201. So if I'm going to write, we'll write it over here, 2.6 and 201. So if I go to my graph and I go up to a height of 206 and I go over to 201, well, guess what? If this is 80, 160 is probably like, well, 160 would be more than that. That'd be double, which means 200 is somewhere over here and 2.6 is somewhere up here. Guess what? I just graphed this point right here, give or take. I'm just estimating. We don't need to be exact for the point of this activity, but if you look, there we go, and I graph this, give you a different color. Look, the slope is a lot less. What does that mean? Big deal, big whoop. Well, guess what? The slope, if the slope of this was, say, which is not, it wouldn't be hard to calculate the slope, 25 divided by 1.3, if I'm looking rise divided by run, actually it's the other way around. The rise would be, if I'm looking at these two numbers, I can do the rise, which would be 1.3 divided by that. Let's just round off. Let's just say it's 1 over 25. That's the slope. That means for every 1 centimeter, or it's 1/25th of a centimeter for every milliliter. So it's barely every, by the way, a milliliter is not much water, right? Very, very small amount of water. But if it's 1 milliliter, it goes up 1/25th of a centimeter for every milliliter. Now this one, on the other hand, if I did this divided by this is roughly, again, I'm just estimating 1/100th for the slope. Rise divided by run. I went up 2 and I went over 200. That's roughly 1/100th. Notice the slope is a lot less, meaning for every, I need 1/100th. I go up 1/100th of a centimeter every time I add a milliliter. Here I go up 1/25th of a centimeter every time I add a milliliter. This one I go way less than that. So why am I doing all that? And by the way, I kind of answered question D. If I pick any of these points, for example, let's switch colors. If I chose this point, like that is this point right here. It says choose a point on the graph and explain its meaning in the context of the situation. Well, you pretty much just need to write that down here. So go ahead and do that. Hit pause if you need to. That shouldn't take but 10 to 20 seconds. But long story short, here is my graph, I just graphed this cylinder, and I also just graphed, stop it, there we go, and I also just graphed, whoops, not that one, the one that was 2.5, right? Whatever. And I graphed that one. So I graphed that one, and I graphed that one, and notice the lines had way different slopes. So what do you think's going to happen here? Look at the graph of this cylinder. This is one, I'm not graphing two, I'm graphing one unknown container. And it also shows the height of the container as a function of its volume. The height depends on its volume. So if that's the case, what shape is this? What shape could this, explain what you think it is and draw a possible container. And by the way, if you need a quick tutorial on, I think they actually do it in the next, it's kind of annoying because they do it in the next lesson. But they don't do it in this lesson. First off, if you draw an oval and you draw an identical oval, and notice those aren't even remotely close, and connect them, you have a cylinder. So obviously you can draw yours much better than mine if you wanted to. But if you were to draw this, notice the slope's like this and then like this. What shape do you think this container is? Go ahead and draw and see what you come up with. When it says explain how you know and draw a possible container, what shape could this container have? And if you're going off of what we just talked about, go ahead and hit pause and draw something. But this container is filling up quickly, and then all of a sudden it doesn't fill up so quickly. It's not that they started pouring more slowly, because we're going to, and I probably should have stated that in the last one, we're assuming that we are filling all these like at the exact same rate. Like we're assuming like our faucet is on full. or pouring out of a pitcher at the exact same rate or something like that. So we're not turning the faucet on less full or anything like that. But, well, and even actually the way this function is written doesn't even actually speak to how fast something is flowing, because it's just height versus volume, not at all versus how much water is coming out per second. So there is no time in this, so forget what I just said. But let's look at this. So maybe you drew something like this. Initially, it's filling up quickly, so you have a shape. And again, you could draw this a million different ways. But there's an initial cylinder, and then it starts filling up more slowly. So that was the first, notice, 9 inches. So technically you don't have to write the distances at all, but technically from there it's 9. And then it goes up from 9 to 13, which isn't very much. But notice I went from 40 milliliters from here, from 40 to 100. So this only took 40 milliliters, but this is taking 60 milliliters. So it's still a good chunk of volume, but it's not very tall. It's only from 9 to 13. So it's probably going to look like something like that's not, well, who cares? We'll draw it the best we can, but it's probably going to look something like that. It's kind of hard to, hopefully my drawing is good enough, but you can see it's kind of a cylinder on top of a cylinder. Notice the second one is a lot wider, not quite as tall, holds a lot more volume than the first one, or it should, but it's just a sketch. So at first it's filling up, the height goes up much more quickly for just a small amount of volume. Then the height goes up much more slowly, even though I'm adding the same amount of water. So you can see that that it gets a lot wider on the top of the graph right here. This part is the wider, and that part is the skinnier section. So that's problem number 1. It's kind of a good little brain teaser. Now here's another good brain teaser. Same question, same everything. Height, there it is. Volume, there it is. Notice we've got one section, slightly different section, and a slightly different section. So it's filling up at, the height is kind of going up versus this. Then it gets a little quicker, very steep. Then it gets less steep than all of them. So what do you think that's going to look like? I'm going to leave it up to you to try to draw that. I'll give you a clue. It's going to look somewhat similar to that right there, except I think there's going to be like 3 cylinders stacked on top of one another. And I'll leave it up to you to draw it, but you're going to have a cylinder that is roughly nine centimeters, and again, you won't get out a ruler. And then the next is just from 9 to 12, that is 3 centimeters. And then you have from 12 to 14, which is just 2. So it goes 9, 3, and 2. And if you're going to all draw like my last one, you'll notice you're going to have a relatively normal size. We'll call that normal. We just need to draw one to get us. Then we've got, it fills up quickly and it's not so tall as the other one. So this is not to scale, but all of a sudden then it's a very short stint. Fills up faster. You'll notice that fills up faster, and it's, the other one was 9. This is only 3 centimeters. So technically that probably shouldn't even be that tall because that's more like half of it. but we're not going to be perfectionists. And then the last 2 inches, so this isn't going to be, but it's going to be wider than all of it. But again, not exactly an artist here. No one ever claimed I was. It's going to be something like, give or take that. The last is just 2 inches, not very tall, but slightly wider than the other one. Maybe it should even be more wider because it is filling up a lot slower. But nevertheless, I think you can answer problem 3 accordingly. And this one's kind of interesting. It says, the graph shows the height versus the volume of an unconed container. What shape do you think this is? I'd be curious to see what you could come up with on that one. That's a curved. That one is curved. The height gets very steep and then it narrows, shallows way off. If you want, go ahead and draw that. I know what I would draw, but I'm going to leave it up to you. If you look at that one and you saw those, and you look at that one, you saw that, what do you think the shape of that container is going to be? I'll leave it up to you. I think I know the shape, but now I'm second guessing myself. Yeah, I don't know. Well, I know it's going to look somewhat like something. I'm curious. If you want, give that one a quick try. Other than that, we're going to take a sneak peek at lesson 11 practice problems. It says cylinder A, B, and C have the same radius but different heights. Put the cylinders in order of their volume from least to greatest. They all have the same radius, meaning the width is all the same. So which one of these is going to hold the most volume? Put the cylinders in order of their volume from least to greatest. That shouldn't be terribly difficult. Problem 2. This is kind of like what we just noticed. Notice there's different steepnesses in these graphs. 2 cylinders A and B each started with different amounts of water. I was trying to question them, like, why are they not starting from 0? I don't know, it says right there. There are different amounts of water. The graph shows how the height of the water changed as the volume of water increased in each cylinder. Match the graphs of A and B to cylinders P and Q. Explain your reasoning. I'll let you figure that one out. I think you can do that. And then problem 3. Which of the following graphs could represent the volume of water in a cylinder as a function of its height? The volume depends on its height. This time, height depended on volume on all of these. They're switching it around. They're saying volume depends on height, which is absolutely doable. The volume depends on the height of the water. Yes, you can switch it around. You could say, well, what's the volume of this? Well, if it's this high, that's how much water is in there. You could easily do that. So if we went back, what do you think that's going to be? I'll let you in a little secret. Not going to be any different than what it looked like already. If you already got a line with a slope and you switched them, the slope might change, but it's still going to be just slanted up. So it's definitely just probably A. And problem 4, together the areas of the rectangles sum to 30 square centimeters. Write an equation showing the relationship between X and Y. Together the areas of these rectangles sum to 30. So that means the area of the first rectangle plus the area of the second rectangle is 30. So that means write an equation showing the relationship between X and Y. So if you remember, area is length times width. So 3 times X will give you the area of that first one, plus the area of the second one, 2 times Y, or 2Y, or Y times 2, doesn't matter. 3 times X, which is 3X. So 3X plus 2Y will equal 30. And I think that's all I need to do for that one. And then it says fill in the missing values. Well, if x is 3, then we can figure it out. If x was 3, that means the area of the rectangle is 9. Or the first one, 3 times 3 is 9. Which means the rest of the rectangle on the right, it's kind of like saying 3 times x. Well, x is 3, so 3 times 3 is 9. Plus 2y equals 30. Plus the second one, this one right here is the 2y. Well, we already know both of them is 30, so if we got rid of the 9, we're at 21. That means 2y is 21. That means 1y is half of 21. So that's kind of how that works. I'll let you finish that out, but other than that, I think I'm going to call it good. If you have any questions, just send me an email and I'll get back to you. Other than that, if you liked, better yet, if you did not like this video, please hit that like and subscribe button. And it really helps out with my channel and whatever else I'm supposed to say. So, all right, keep it real. Peace.